Hey, we have here today a really interesting integral on the board. We have the integral from square root of 3 over 3 to square root of 3 of arctan x cubed over x squared plus 1 dx. When I first looked at this problem, I was thinking, okay, we have arctan, and the derivative of arctan is actually 1 over x squared plus 1 dx. But because of the x cubed, it kind of defeats that strategy. Okay, for the first step, I want to just look at these bounds, and I want to rewrite square root of 3 over 3. We can actually write this as 1 over square root of 3. So we have a nice relationship in the bounds. And because of that, that's going to inspire my substitution. What I want to do is I'm going to make my substitution u equal to 1 over x. Then solving for x, we have just x equals 1. Solving for x, we have x equals 1 over u. I'll take my derivative, and we'll get dx is just minus 1 over u squared du. Now I'll make this substitution, and again, this is pretty nice because when I plug a square root of 3 in here, we get 1 over square root of 3. We plug 1 over square root of 3 in here, we get square root of 3. So it actually just flips the bounds. Then for the numerator, our arctan, this will become, because x is 1 over u, this is going to become 1 over u cubed. And then x squared is going to be 1 over u squared plus 1. Then our dx value, we're going to have minus 1 over u squared du. And here we have a few things to do. I'm going to take this minus sign and bring it out front and just use it to flip these bounds back. So that's going to put our bounds back to the way we had it originally. Now I'll rewrite this with our new bounds, but I'm going to distribute in this u squared. So when I distribute in u squared here, we're just going to have 1, and we distributing in u squared here, we're going to have a u squared du. And for our numerator, I'm going to use an identity. Let's just take a look. Okay, over here to the right, we have this identity for arctan of 1 over x. And so arctan of 1 over x is cotangent of x, or you could do the same thing with cotangent. So making use of this first formula, we'll write this as inverse cotangent of u cubed. Okay, from here, what I'm going to do is a variable change. I just want to get everything back into x so we can add these integrals together. It's a definite integral, so I can change the variable to whatever I want. Then from here, what I'm going to do is let's just call our original integral I, and we'll call this integral I. We'll add these two integrals together because we're in the same variable, we have the same denominator, the same bounds. Now adding this together, you may think this integral looks worse than what we started with. Well, the thing to notice really is this numerator that's very interesting, that we're adding inverse tangent to inverse cotangent, and we do have a formula for that. We have this formula over here to the right that says arctan plus arccotangent is equal to pi over 2. Well, this is going to work for any angle at all. So we've got x cubed here, but this is still going to work. Our numerator is actually pi over 2. So using this and just rewriting, I can put pi over 2 in the numerator, but that's just a constant value. So what I'm going to do is bring it out front of the integral, okay? But that means our integral has just become dx over x squared plus 1. And the beauty of that is this is a very familiar integral. We know how to integrate this, so this is going to allow us to finish this problem off. So from here, what I'll do, I'm just going to divide by 2 right now, so that when I rewrite this, we're going to have, dividing 2 here, we're going to have pi over 4 out front. Integral of dx over x squared plus 1 is just going to be arctan. And we just need to evaluate this from square root of 3 to 1 over square root of 3. And arctan evaluated at square root of 3 is just going to be pi over 3. And arctan at 1 over square root of 3 is just going to be pi over 6. Well, we can take pi over 3 and write it as 2 pi over 6, so that this whole thing is actually just pi over 6. Then just multiplying pi over 4 times pi over 6, we get our final solution, which is going to be pi squared over 24. After doing this, the thing that really jumped out to me was this exponent really doesn't matter at all. You know, let's say this was 99, or let's say it was a million or whatever. The reason the exponent doesn't matter here is because the exponent doesn't matter here, because whatever this angle is, this numerator is always going to be pi over 2. So what I had in mind for a shortcut, since this exponent doesn't matter, why don't I just choose whatever I want it to be? So instead of integrating it with x cubed, why don't I just integrate it with x? So over here, if I'm assuming my exponent's just 1 and we're just integrating tan of x, then this is actually a pretty routine problem, as we make a u substitution for arctan x, and our du is just dx over x squared plus 1. So this becomes a very easy problem, as our integral just becomes u du. Integrated with power rule, you get u squared over 2. And then doing that, you can very quickly get the answer of x squared over 24. So you get the same answer and you'd have an easier problem. But then I was thinking, if I can really choose the exponent to be whatever I want, why not just choose it to be 0, right? So if I choose this exponent to be 0, now we have in the numerator just tan inverse x to the 0 is just 1. But then tan inverse of 1 is just pi over 4. So what I can do is bring pi over 4 in front of the integral, and then we're just integrating right away dx over x squared plus 1. We know what that is. That's going to be arctan. Evaluating this is going to be actually the same thing we did earlier. Arctan at square root of 3 is going to be pi over 3 minus pi over 6. And this thing's going to be pi squared over 24. So I think this would actually be the fastest way, where you're basically just eliminating the arctan altogether and integrating dx over x squared plus 1. One thing I need to add, though, is to be able to do this, you need to be able to recognize pretty early on that the exponent doesn't matter, and then that would allow you to skip the longer method and go right to this. Anyway, thought it was a really interesting problem today. We'll stop it there. Thanks everyone for watching. Have a great day.